Welcome back to the third part of the workshop, and we'll now concentrate on the highlights. We are going to have a view to this charging simulations of the half cell. We'll make a fast estimation of a charging curve. We are going to build a battery, and we'll look at different solvers that are possible. If you had some problems before in the workshop, or you just want to do part 3, that's no problem. You can easily just go to the intermediate structure folder. It's 03, and here you load structure for part 3 via drag and drop, or you go to the analysis folder. I can also show you here the analysis folder, and here you can have all the results we are going to produce in the workshop with the corresponding structures, and we can easily drag and drop them into Geodict and then load the structure and load also the results. So it's easy to start the workshop from here. As the charge half cell simulation should be ready now, we can have a view to the result file. And here first we see that the simulation was successful, the first message, and we see that there's no warning, so everything was fine. And we can view to the time-dependent charge curve. So here we see the time, we see the electrode state of charge, we see the cell potential, the equilibrium cell potential at cell SOC, the charge rate and the transferred charge rate after time. We can go to the plots, and here several of the data that we calculated are directly plotted. You can edit the axis, you can edit the graph style, for example, if you want to have bars, lines, points, or something else. And you can also save the image if you like it just the way it is, or you can make check marks which potentials in which steps you want to have shown. And here we can change the cell potential over state of charge, over capacity density, over time. We can have the electrode state of charge over time, the capacity of the electrode over time, and a lot of different plots. Here you can see everything of that. When we go to lithium concentration, we can see where the lithium in the position in the electrode is moving, and we can see this in different state of charges. We can see the potential of the solids and of the electrolytes. We can also see the overpotentials, and we can see that there's a peak, for example, and then we can maybe also ask some questions. Why are the curves just like this? And we also get some information about the battery geometry, where, for example, the porosity is, how big the porosity is near the separator, or in between, in fact, the collectors, and the metadata. Okay, here we can choose the cell SOC at which percentage, and we can, if we stay at the full charge, we can click on load the cell. Here we see all the values that will be loaded. So that's the diffusion flux, it is the electronic current density, it is the potential solid, it is the ionic current densities. All those volume fields are going to be loaded, and if you click on OK and we wait, then we can see those volume fields. I think the structure we haven't viewed already. So here we have the grains of the cropped structure, we have the binder, and we have here the collectors and the anode lithium reservoir. And here we have the volume field. And now I'm going to show you how to do the right clipping. To do so, we take a nice view to the cell, and then we proceed the same as we proceeded for the streamlines. we first unclip the volume field and we have a look to the electrode, to the battery we were building. We go on structure and we can use the clipping. We start with invert again, and then we look, okay, this direction is not so well. Then we can make here the half, or we can make the Z direction. Click on 25, and then it's the half, the cell is full. And you can see that the cell is half full. And now we clip on the volume field, and we are going to do the same. Click on invert, go to the volume field. So, and for the volume field we do the same, 25 here, and going to this side. So now it's right. After doing some mistakes, I think you also did it the right way, or you could play a little bit around. So now we have here, we can choose which one do we want to have seen. The diffusion flux is not so looking so interesting here, for example. That's why we go to electronic current density, and we choose this one, and we make the transparency, and we click on the visible material IDs, and we make the pores not visible to see where the electronic current density is located. We can have a short view around to see that the density is very near to the grains. If you're curious, you can also go to ionic current density to see what is going to change. You can see here, or you can go around the potential of the electrode. It is here red, and there's a high potential, and the blue is a low potential. There's several different potential for the solid. You can look around what is going to happen. And I think it's a quite good visualization to understand what happens in the cell. Now we are going to set the full charging profile, and I show you firstly how to do it. We first go to edit, and we go to experiment, and we choose the set a charging profile. And when we make the window a little bit bigger, you can here set a charging profile. You can choose charge or discharge. You can choose the charge rate, or current density, current or cell potential. You can look which BC value will be applied. You have a view to the stop conditions and the stop cell SOC, or you can also make the stopping condition after time. And you set the profile, and we will not run this because it's needing too much time, but we'll have a view to the result file. So we go now on cancel, and you open the handout analysis, 72, and you go until you find the geodict result file, charge half cell, charging profile, and you're going to load this via drag and drop into geodict. And here you can now see the results of this charging profile you've been setting in. In red, it's the first step, and you have the start point and you have the end point. So in the end, it is falling down again. And you see the electrode state of charge. So how is the cell potential changing for those steps? As next topic of this workshop, I want to show you the settings for full battery simulation. And to start for this, we build up a battery. For this, we are going to use design battery. You go to predict. You go to predict, go to design battery, and then you click on edit. And here you see that there are some default materials loaded in for cathode and anode material. Here I can show you what is important. Important is that the material and the cropping is fitting together, so it must be green for both lengths. The voxel length is important, the size of the scan is important. So, but as they are for both the default structures, we can now use the current structure, and we see here that we have a different voxel length and we have the smaller size, and this one is not fitting to the anode material that we have as default in Geodict. And this is why we now use another topic. We go on cancel, then we go on Geo app and make the Crane Geo. We choose this one. We can also go on Crane the model and go on here Crane Geo, and then on predefined, then we come to the same drop-down menu, and for the predefined we are choosing the electrode geo anode. We choose this one and we go on edit. Here we can now predefine what we want to have, and we want to have the active material 1, graphite is totally right, it's the one we want to use. We have no active material 2. The number of voxels in every direction should be 50 because it has to fit to the material before. The SVP is 55, that's right. The binder SVP is only 5%. We have to click on manual here, and we have to set the voxel length to 3.7, and then we can control all the fields and click on OK, and then we can click on run, and we can create the anode. So now we can go back to predict, battery dict, design battery, click on edit, and we can here load the structure, use current structure for the anode material. It still does not fit to the cathode material because now the cathode is not the one we wanted, but here it's white. But before we change the cathode, we see that the plates are not parallel to the separator, so we have to permute structure. So we click on cancel. So we have to change Z and X direction. So we go here on structure, we click on process, we click on permute. The rotation is not helping, we have to go to permute, and we have to permute the X and Z direction. Click on run. And now if we use current structure, we see that it's parallel the plate to the cathode material. So now we can browse, and we can go to the handout folder. So I'm go on browse and go on browse, and then I open the folder for the handouts, and I take the structure for part 3. I load it in, and now I see that the voxel length is fitting, that the size of this the scan is fitting, and that the structure is fitting together. And I can click on OK, and now I can click on run. And I'm going to make a backup. So now I see that the result file is opening. So we have the result and we have the electrolyte, we have the material, the volume percentages, and in fraction. We can have the plots here where we can see where porosity is and where material is. And here we see where materials and where pores are, so that's just inverse. When we minimize that, we see the battery in new colors. And we can look from every direction to this. And we can proceed now with the analyzing of the battery. To do this, we go on Analyze Battery and click on Edit. We can analyze battery with symmetric or periodic conditions. And we let the symmetric, and we have the binder that's porous. We click on OK, and we click on Run. Also overwrite this because I did it before. And now we see how good the connection between the material is. For example, we see that the anode active material is just to 5% connected and almost 20% are not connected. And for the cathode active material, there's a much smaller part of unconnected material. And if this value is that high, the reason is that we have a very, very small anode, so we don't worry for the workshop, but normally I would look at this value again. With this information, we prepare the charged battery simulation, and we do a calculate estimation only before. For that, because the charged battery simulation is a very long simulation, and if we calculate an estimation only, we can have an idea about the quality of the simulation without calculating too much. So it's CPU time saving and also just normal time saving. And to do this, we go on Charge Battery. We click on Edit, and we click, we let all the defaults. And on this window, for the output options, we click on Calculate Estimation Only. We have the 10%, and we click on OK. And then we click on Charge. I can also overwrite this because I did it before. And I got an error message because there's a lot of unconnected material. I'm going to ignore this for this workshop now, but maybe the simulation results will not be the best. And it's charging now, and we wait some minutes, and we can see the result file where the warning is written bigger, and that's quite well, because like this we avoid doing some mistakes. We can go on plots and can have a look to the charge curve where the estimated cell potential is, like this. And we now, of course, want to compare this with the cell potentials of the full cell potentials. So we go on to the project folder, or the analysis folder, and we have here a geodetic result file, charge battery full, and we're going to load this one. And we can now go down and select both of them. And here we see the estimated cell potential. We see the full charge cell potential. We can combine the results to run. Click on override again. That's a little bit smaller. Here, it's loading. And here we can see that those results do not distinguish quite much. So we really have a well estimation that we can use, and this is a very time CPU saving tool that should be used quite well and quite often, I think. If we go back to charge battery I also want you to show something. We have this create video tool where you can edit parameters, how many frames and about the video. And we can make a battery video where the simulation during charging or discharging can be visualized. And it's a nice topic if you want to make some presentation for externals, for example. We now finished the workshop, and I want to summarize what you've learned during the last 1.5 hours. You learned how to make an import and segmentation of micro CT data or FIB-SIM SEM data. You learned how to analyze the geometry to calculate the transport properties and the cathode material. You learned 2 methods to calculate the pore sizes. And you know how to calculate tortuosity. You learned the new module charge half cell, and you've been building a battery half cell, and then you did some charging simulation on the half cell. You learned how to build a battery, and you learned the fast estimation, the new tool. The different solvers that are now inside the battery dict, and you had the different charge weights. Now I want to say thank you from the whole Math2Market team, and with special highlights also on Andreas Wiegmann, who is our CEO. If there are any questions, just ask. I will be here and wait for them.